So, welcome to the Vodcast about titrations, and similar to that which we had done with buffers, you will need to find a handout that looks like this. Now, you actually have two choices. You can find the blank handout that looks like this and be writing in information and stopping the vodcast as necessary. Or, if you go to the agenda, you will see that I've made a PDF of my solutions to this handout and posted it with the link on the agenda. That way you don't have to write, you can just focus. But I do have to say, when you're studying AP Chemistry, when you use all of your learning modalities, you see it on the screen, you hear me explaining it, and you are writing, that's how you learn the tough concepts in AP Chem. So I'm going to skip over this part right here because you've already done a titration and you know that it's a volumetric analysis that involves, in our case, acid-base neutralizations, and you did an oxidation and reduction one back in the fall. What we are going to do is focus on the kinds of titration curves you could expect to see in an AP question, and also to be able to do calculations to determine the pH at any point along the titration. So this is the titration of a strong acid with a strong base. You can always recognize it as you look at the four regions, because the initial pH is very low, less than 1. That means we've got 25 milliliters of 0.2 molar hydrochloric acid, and it completely determines the pH at that point. When you travel from the initial, as you drip in sodium hydroxide, this bottom axis was not labeled. It should say 20.2 molar NaOH. Now when you go from the initial point up to the equivalence point, your pH is going to be determined by how much of your acid has not yet been neutralized. But at the moment you reach the infamous equivalence point, then the pH of a strong base and strong acid only equals 7. And the moles of the acid equals the moles of the base, but no hydrolysis is taking place. You've just made salty water at that point. If you continue to add sodium hydroxide after that equivalence point, then your pH is going to be determined by whatever amount of excess hydroxide is present there. Notice that when we use phenolphthalein on an indicator, you want the change of the color for the indicator endpoint to be in this steep region here encompassing that equivalence point. And that's not necessarily exactly equal, but a good enough indicator, as we'll see here in just a moment. Okay, so before I've added any NaOH, simple. I take the negative log of the initial ion hydrochloride concentration or hydrochloric acid, and I find the pH is less than 1.7. When you do the next calculation, after you've added, let's say, 10 milliliters of NaOH, we have to do that thing I talked about before, where first we dilute, then neut. What that means is that adding 10 mils of NaOH to the original 25 milliliters of the acid means you have a new total volume. So I'm going to find the molarity of the hydrochloric acid by going molarity times its original volume divided by the new total volume, 35 milliliters or 0.035 liters. I like to change to liters to be consistent because that's what molarity is based upon. But if this said milliliters and that said milliliters, it won't make any difference. I'm going to do the same thing for the NaOH, but I've added 10 mils of NaOH, so I've got 0.01 times 0.2, that's its molarity, divided by 0.035. Now I have the two concentrations. This isn't an equilibrium thing because you can see that I have way more acid still than base, so all of the base gets neutralized. I lose a little bit of my hydrochloric acid, and to find the pH, it's simply negative log of 0.086. So far, we've gone from 0.7 up to 1.07, and that's not a terribly large increase in pH. Let's add another bit more of sodium hydroxide. And this time, if you look at the graph, you can see that the equivalence point is at 25 milliliters. So let's just stop short of 25 and add 24.9 milliliters of NaOH total up to that point. I do my new total volume by adding the original 25 of the acid plus the new 24.9 from the base. I take molarity times volume divided by the new volume. 49.9 milliliters is 0.0499 liters. There's the hydrogen chloride or hydrogen ion concentration. Same thing for the base, 0.2 molarity times 24.9 milliliters or 0.0249 liters divided by the new volume. Now I've got the molarity of the base is 0.0998. I still got more acid than base. There's a little bit of hydrogen ion left here, so the negative log of 0.0004, I've gone up to 3.40 pH. If you were actually doing this titration like you had done last year, the next step is the part that was maddening for you, because you were being so careful dripping in your little drips of acid, and all of a sudden the thing went like super bright pink, and you'd only put in the tiniest bit of a drop of acid. And that's why you, just before the equivalence point, it'll be clear, 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 and then the moment you hit the equivalence point, that phenolphthalein does its thing, and actually it only takes about 0.01 milliliters of additional base to make you get to that equivalence point, and I think that was something like a third of a drop or something like that. It's really, really tiny. So the pH is going to change by 5.2 points, because here it is like 3, and we've got to get up to 7, so it's going to show a dramatic change at that point in time. Another kind of graph you might be expected to identify is the titration of a weak acid by a strong base. Notice that our initial pH, still determined by the Ka now, is higher than 1, so we're starting about 2 or so. When you go from the equivalent, so from the initial up to but not including the equivalence point, it's acting like a buffer right here, so we'll be using our buddy Henderson-Hasselbalch. At the equivalence point, the pH is not 7. At the equivalence point, the titration of a weak acid by a strong base is greater than 7, or 8.87. And if you continue to add more NaOH, then the excess sodium hydroxide would be what would determining the pH is going to be. So I know you memorized the Ka of acetic acid, but there it is. And just a side point, you can write acetic acid this way with its accompanying conjugate base acetate ion, or you can write it hydrogen acetate, and this is the hydrogen that would fall off, leaving this way of writing the acetate ion. Either way works. I'm writing it like this because you can see there's a carboxylic acid with a C double bond OH stuck at the end of a chain of carbon atoms. Okay, so at the start of the titration, you had 25 milliliters, it's up here in the corner of the curve, of 0.2 molar acetic. So I don't need to worry about the volume, but this time a weak acid undergoes hydrolysis, so I had to show an equilibrium equation happening, and I had to write a Ka expression. I'm going to let the concentration of the hydronium and the acetate to stand for X, because whatever the acetic loses in hydrolysis, that must equal what these increase in concentration, yet they started at 0. So it's your classic Ka equals X squared over the original, small Ka, ignore the X squared over 0.2 molar. Solving for the square of that value, I find that X equals 1.9 times 10 to the minus 3. That could represent the hydronium, and I take the negative log and find that the pH is 2.72. That's where we're starting right there. Okay, now that I have the initial pH, let's start adding some sodium hydroxide. When you start to add NaOH, forget about the Na. Don't put it in the equation. And we're looking at now in a situation where acetic acid is being attacked by some hydroxide. You know, of course, that it's going to give that hydroxide a hydrogen to turn it into water, which we don't care about, leaving behind that way of writing the acetate ion. We still have to add the original volume with any additional. So we started with 25 milliliters. We've added 12.5 of the base, So now we have a new total volume of 0.0375 or 37.5 milliliters. I take the molarity of the acetic acid times its original volume, divided by the new total volume, and the molarity of the acetic is 0.133. For the base, sodium hydroxide, a strong base, not to be confused with the conjugate base, it's 0.2 molar times its 12.5 milliliters, or 0.0125 liters, divided by the new total volume, 0.067. You always have to stand back and look who's bigger. Acid still is greater than hydroxide, so all the hydroxide gets neutralized. I have a little bit of acetic acid left, 0.066, and whatever amount these guys decreased by, the acetate increased by that amount. And now it's time for me to pull out my buddy, the Henderson-Hasselbalch. It's Henderson-Hasselbalch time. So pH equals the pKa of the log of the base over the acid. The base means the conjugate base of acetic acid, 0.067. The acid is what's left of the acetic acid, 0.066. And what's kind of cool about that, if you probably have done your buffer calculations by now, which I hope you have, in preparation for the lab, that's pretty much the log of 1. And the log of 1, you can write 1 as 10 to the 0, and a log is the power to which 10 must be raised to get that number. Well, that's just 0. So essentially, what we have is the pH is equal to the pKa after we've added that amount, 12.5 milliliters of 0.2 molar NaOH. Now notice if you look at the graph, and I'm taking a look at mine, see how that particular graph's equivalence point happens when you reach 25 milliliters, and we've added half that amount. So this is an interesting concept. When you're doing this, the pH will equal the pKa when you've gone halfway to the equivalence point. If the equivalence point was at 25, if I go halfway to there, that's 12.5 milliliters. That's when pH equals pKa. Come back to that guy at a later date, but hang on to that thought. So now the calculations that I have to do at that point in time is treating that as if it's a buffer up to the equivalence point. Let's go to the equivalence point. And there's a major typo right here, so fix that please. This should say acetic acid, not hydrochloric acid. I don't know what I was doing there. So when you reach the equivalence point of the titration, what we've got is we have to calculate the pH of a solution who's made a salt that's going to undergo hydrolysis. That's why we did the hydrolysis lab. So let's see. We would have had to get to that end point. We would have had the original 25 milliliters of the acid times its molarity, and the 50 milliliters or 0.05 liters came from here. They added 25 milliliters of base to the original 25 milliliters of acid, and you can see that on the graph itself. Go to where the vertical endpoint is, or inflection point is, and just look down and you can see 25 mils of base have been added. So the new total volume is 50 mils. I'm going to take 0.2 molar times its 25 milliliters or 0.025 liters, and I can find out that the concentration of the acid and the base are the same when we're at the equivalence point. So we've got each of them totally neutralizing each other, so nothing's left, but you are making a salt. Now I put the sodium in parentheses here because I don't really care about the sodium. It's always a spectator, and putting it in there just confuses things. But the bottom line is you made an acetate ion. And you know from the hydrolysis lab that it would undergo hydrolysis. So what I'm going to do is note that I've got 0.10 molar of just acetate in there. And this is the expression of acetate ion, a weak base undergoing hydrolysis by accepting a hydrogen from water, turning back into acetic, and forming some hydroxides. So what we need now is, if it's acting as a base, we're going to need that guy's Kb. We weren't given the Kb of acetate, but I can use the Ka of acetic, and that handy dandy little method that you learned, 1 times 10 to the minus 14th divided by the Ka, gives you the Kb. Now I'm back to one of those deals where I have to write Kb would be equal to x squared over the original concentration of the acetate, 0.1. Remember, it got formed here. And then when I solve for x, I get 7.46 times 10 to the minus 6. Well, look back at your equation. There's no hydrogen or hydronium in there. There's just hydroxide. So you're going to have to go the route to find POH and then subtract from 14 to find pH. And this is where I always mess up again. So POH is the negative log of 7.46. That equals 5.13. And when I take 14 minus 5.13, there's my pH. And I think it says something in there that the calculation should equal 8.87. I think we did pretty good. So that's what's sort of different about this. The pH at this titration using a weak acid with a strong base is greater than 7. So there is a picture which we will not do any calculations with that shows the titration of a weak base with a strong acid, and as you would expect, it looks kind of the opposite. If it's a weak base, it won't be at pH of 14. It'll start initially somewhere like around 12-ish or so. As I add strong acid to it, the pH will continue to drop. The inflection point of both weak base and weak acid titrations isn't as long right here as it is on a strong acid, strong base titration. And when this guy reaches the equivalence point, not equal to 7, it's a little bit less than 7. It's more acidic. So we still have to do the similar kind of calculations. Here it's acting as if it's a buffer, except this time you have to think about it as it's a ammonia, which is what you started with, which is a weak base. So you'll be forming ammonium ion, NH4. We don't care about the chloride that's there. And so you'll have to be looking at this particular section right here, like we had done on the previous slide. You could do at the equivalence point, at the point before the equivalence point, you could use a Henderson-Hasselbalch again, except you'll have KBs, not KAs, so you have to be careful with that. But you'll be in the same position when you're there at the equivalence point. You will have made ammonium ion, which undergoes hydrolysis, and then you would do a calculation similar to the previous, where we had a conjugate base undergoing hydrolysis. Well, ammonium is a conjugate acid, and so you'd have to get a Ka if you didn't have it, go through a calculation similar to here, and other than going in the opposite direction, it is the same kind of calculation. Beyond the equivalence point, the pH will be dominated by having excess strong acid there, so you only need to know the concentration of the hydrochloric acid and take the negative log of the hydrogen ion. That's about it for titrations. I hope you found this helpful, and we'll see you next time.